So this is the Senior Math Challenge from 2024. Let's just go straight into it. Now you can do the whole let x equal 0.25 recurring thing and then find 100x and take it away. Or you can just memorize that if you've got two dots like this above it, it's just this number over 99. So this is 25 over 99. When you're finding two fifths of that, you can obviously cancel these fives to make 2 times 5 over 99, which is 10 over 99, and then use the backwards logic to say that this must be 0.10 recurring like this. Again, you can do that long way around if you want to, but memorizing some of these results is quite helpful to speed you up. So we'll approximate these things. This is approximately this, which we can write in standard form would probably be easiest, and then we can approximate this, again in standard form, probably easiest. And then we just need to divide this by this to find out how many of these are in there. Of course, 3 minus 5 makes 10 to the power 8. So we end up with roughly 2.5 times 10 to the 8. So we're looking for to have 7 zeros after 2.5, or roughly 2.7, I guess, and so we'll have the answer of A. Question 3, then, you need to know something about dice to make this question work. Firstly, of course, the total on 2 dices is 2 lots of 1 plus 2 plus and so on, which is 42. So we're missing 9, right? So there are the 3 numbers that are missing, 1 on the table and 2 in the middle, which are the same. They together make 9. There's 2 ways you can do that. You can do 4, 4, 1, so the 4s are in the middle together and then the 1 facing the table, or 2, 2, 5. Now, which of these is it? Well, you need to know that dice, the opposite numbers on dice, always add up to 7. So if 1 was on facing the table and 4 was above it, that doesn't work because they add up to 5. So it must be this case here, which is the answer of B. Question 4 is super easy. It's just obviously this plus this plus this makes 180, and you can just solve your quadratic and factorize and get the answer of x equals 10, which means the largest angle is 100. So that should be fairly straightforward. Question 5, just to try and do this in the least painful way, right? This is the same as 2 to the power 10 because 4 is 2 squared times the powers together. 2 to the power 10 is 2 to the power 6 times 2 to the power 4. And then these two things now have the same power, so we can say this is 2 times 5 all to the power 4. 2 times 5 is 10. 10 to the power 4 is obviously just 1 with 4 zeros at the end. And then 2 to the 6 is 64, so this is just 64 with 4 zeros at the end, which is 6 digits in total. Not got really much to say about question 6, other than you just need to get an octagon and then make a cone out of it. So that's clearly going to have 8 edges on the octagon itself, and then 8 more to get to the point at the top of the cone, which is 16 edges in total. Kind of just logical that that's the absolute best you can do, so I'll just leave it there. Question 7, difference of 2 squares. And then, of course, this one is 81 minus 1, this one is 81 plus 1. 82 is 2 times 41, and it's pretty clear there's not going to be a larger prime factor than 41 in this one here. So the largest one is just going to be this 41 here. If the mean of these numbers, or 4 of these numbers, is 11x, if there's 4 of them, then we just need to times this by 4 to find the total, which is 44x. Currently, these things add up to 60x, so you need to remove 16 to make a total of 44, and so D will be our answer. To be divisible by 18, you need to be divisible by 2, which means ending in an even number. And you also need to be divisible by 9, which means your digits need to sum to a multiple of 9. So the highest even number we can end with is clearly 8, which means we must start with 8 because it's palindromic. Now, we don't really have much rules to follow here yet, so we just want to shove some 9s in to here and here because that makes the number as big as possible. And now we need this digit sum to be divisible by 9. Currently it's 34, so the multiples of 9 beyond there are 36 and 45 and 54. Clearly can't get to 54 because that would require 2 10s. Can't get to 45 because that's 9 more. Sorry, it's 11 more. And we can't use 2 5.5s, right? So we just need to use 2 1s to get to 36. And so the middle digit there is just a 1. Question 10 then, the prime factorization. This question disgusted me because it's everybody's homework before they do the SMC to learn the prime factorization of whatever year they're in, and so to just give it to you is truly atrocious. In any case, we can just work out this by just taking some of these primes. So basically, if we take, say, the 2 and the 11, that gives us a factor of 22, and then its factor pair will just be everything else in this list together. But that's 22, then we can take 2 2s and 11, that's 44, so that would be one of them. 3 2s and 11 even works because that gets to 88. You can also just take 11 on its own, you can take 23 on its own, or you can do 23 times 2 or 23 times 2 times 2. You can't take any of the 2s on their own because they don't make double digit numbers, and you can't do 11 times 23. So we just have 7 of these, and the answer is 7. To make a square number, we want some object, some algebraic object, all squared at the end. By the way, this is the prime factorization, in case you're watching this for 2025, this is the prime factorization for this year. Please learn it because they probably won't give it to them. They usually don't, and so yeah, learn this. Anyway, we want something squared here. So clearly none of the ones that have an odd power of n as the leading term are going to work, because how do you get something squared to be 3 overall or 5 overall without using a fractional n, which would defeat the purpose of this being a positive integer being squared. So it's clearly just these two. You can either expand this out to find that, which clearly doesn't factorize to a square, or you can just shove in 1 and note that that's not a square number. And in any case, the answer is D. We don't need to work out exactly how that works. It's only the last one left. We have 2-digit primes here that between them all use the digits except for 5. Now, if they do that, then all of their last digits must just be all of the odd numbers, because we can't put any even numbers as the last digit to make a prime unless we're just making the number 2, but 2 isn't isn't 2 digits, so that's fine. So these have to be all the last digits. Now, if you want to, you can find a way to arrange the 4 even numbers that are left in order to make a bunch of primes. And I actually did that, right? You can't put the 2 here because that makes 21, that's not prime, but you can put it there. You can put the 4 here because 41 is prime. You can put the 6 here, I think, because 67 is prime. And you can put the 8 here. That might not even be right. It also doesn't even matter because the objective here is to add up all the primes together. And if you think about this carefully for a second, it doesn't matter what order you put any of the even numbers in. They're still going to add to make the same thing. Because this is just going to be, let's say we put the 2 here. It's just 20 plus 1, and then 40 plus 3. It doesn't matter whether the 4 goes over there. It's still going to be 40 plus 9. And so when you add everything together, it's still going to make whatever total sum it always makes. So basically, as soon as you realize you can put the odd numbers here, you can then just do 1 plus 3 plus 7 plus 9 plus 20 plus 40 plus 60 plus 80, and it makes 220, and that will be the answer. For this one here, just put A and B down at the bottom here. This box has to be A plus 1, this one has to be B plus 10, this one has to be Z plus 1 plus A, and this one Z plus B plus 10. And then we can say that 2024 equals this plus this, of course, but of course A plus B is itself Z based on this bit here, so replace that with Z, tidy up some numbers, and you'll end up with doing a bus stop and getting Z is 671. Nice and straightforward. Another thing about primes here, this one is much less nice. We know that T and S are going to have to be 1 and 3 because primes can't end in 2 and 4 or 5 unless they are 2 and 4 and 5, but sorry, not 4 of course, but these are 3 digits, so okay, it ends in a 3 and a 1. And now I just decide to try all of the combinations, so put the 2 in the middle, put the 4 in the middle, put the 5 in the middle. And now here, for these two, you've got the numbers 5 and 4 left to put in some order, and here you've got the numbers 2 and 5, and here you've got the numbers 2 and 4. Now, the only way that I saw of getting rid of some cases here was to think about the digit sum. If the digit sum is a multiple of 3, then it's not prime. So I wrote out the possible combinations of numbers that have a digit sum that's a multiple of 3, and we can't use any of these combinations in any order because they add up to make a multiple of 3, and therefore they're not going to be prime. And that actually gets rid of this entire middle row, because if you put the 2 here, you get 2, 4, 1. And if you put which means putting the 5 here, but 5, 4, 3 is on the ban list. And if you put the 5, if you try and put the 2 here, 2, 4, 3 is also on the ban list. So this one just doesn't work at all. This one sort of works. You have to put the 4 here and the 5 here to evade the ban list. And then this one also sort of works here. So which one of these is right? I didn't find any useful way of doing this. There isn't any other really good prime test. The next easiest is the 11 one probably, which is the alternating digit sum. And actually what you can notice is that this one fails it. 4 minus 5 plus 1 is 0, so this is divisible by 11. And so therefore this is not the right one, and this is, and 2 is in the middle. That's probably, I didn't find any other way of easily telling whether any of these are not prime, but that's probably the easiest way, using that alternating digit sum. And when we get back to a nice question here, call this small square, x, side length x, the big one y. You know that y squared minus x squared is this 62 that they've given you, but you also know from this NL being 10 that this whole thing is y, obviously, again. So y squared plus x squared is 10 squared. Of course, we can just rearrange this one for y and just shove it in here. And then when we do some arranging and dividing, we get that we have root 19 as our answer. And a very easy question. This one, you just need to find an efficient way of counting the ways to do it. So maybe we'll start by having all of the reds in the corners. So if you put all 4 reds in the corners, I'm not sure why there's not another red coming up. Oh, it's a bit late. Oh well. So if you put all 3 reds in the corners, then there are just 4 ways of doing that, right? Because you just evade one corner, so there's 4 different corners you could not mark. So there are 4 ways to put all the reds in the corners. Now, if you get to the second setup where you put a red on 2 different rows like this, so a red here, or a red here, or a red here, or a red here, so just using 2 different rows but also still the corners. That's 4 ways of doing that, 4 ways to arrange the R's such that each one is in a different row. And now there are only 4 other places to put the r's. I just want to put them somewhere in these middle 4, because if I try, for example, to put it over here, then I overlap with this case up here, where I've already got 3 r's looking like that. So I have 4 cases to put the 2 r's in 2 separate rows, but also in the corners. And then the third r just needs to go in the middle to avoid the 3 corner case that we've already counted. So that's going to be 4 ways, 4 setups each, that's 16 in total. And the last way is if you set up the 2 initial r's in different, in the same row. So like this, there's only 2 ways to do that, right? This, or this. And again, the last r just needs to go in one of the other places, in one of the other 2 places. Can't go in the corner because we already counted the 3 r case. So either this and this, where the other r goes into one of those 2, or this and this, where the other r goes into one of those 2. So that's 4 ways from there, and then it's just 4 plus 4 plus 16, which is 24 total ways. Just set up an equation here. You've got 4 balls. Let's just call n of them red. So n over 4 times n minus 1 over 3, because you don't put the thing back, equals a half. You just solve this quadratic. It's not hard to do. You get n is equal to 3. And therefore there are 3 reds and 1 white. If there's 1 white, the probability of taking 2 whites is obviously 0, and that'll be our answer. Lovely question here. Every region here is equal. There are 14 of them, which means, of course, there are 10 going around the outside. So that means that, and also we can work out the area of the lighter grey regions by just doing pi times 1 squared divided by 4. And of course, that means that all of the outer regions are also that same amount because they're all equal. Now, because there are 10 of these regions going around the outside, that means that the angle going through them like this is 36 degrees. And so now we can just set up that this area here is pi over 4, because all the areas are pi over 4, as we said, but it's also equal to the large sector, which is 1 plus x all squared times pi times 36 over 360, which is the same as 1/10. Take away the small sector, which is pi times 1 squared times 1/10. And then, of course, we times everything by 10, we add 1 and the square root. And then after a bit of rationalizing and fixing, you end up with the answer of C for that question there. Okay, 5 friends are doing this. There's not any really easy way to do this other than to list them all out. Paolo obviously has 1 and 3 because he can't have 2 and 2, and that's the only other way to make 4. And then we just list out all the other people. So here are the options for Thomas, and then for Quinn, and then for Stephen, and then for Romy. These are just all the options. I just went through it as systematically as I could, going in towards the center or out towards the edge. I didn't list 3 and 8 over here because 3 has already been used. At this point, we just need to look at the options here. Paolo has card 2 is obviously false, so get rid of it. Quinn has card 3 is also obviously false because Paolo does, so get rid of it. So now we just have to test Romy has card 5. So let's give Romy card 5, which means Thomas must have this one because he can't have 11, which means Stephen doesn't have 11, and he also doesn't have 12, so Stephen must have 9 and 10. And then is there anything left over? I think Quinn can have 4 and 7, and this all works out perfectly. With no overlaps, so therefore Romy has card 5 is an acceptable answer. I don't even need to check the other 2 options because there isn't an option that says we don't know. So if we found a setup for C, then it must just be the right one. There's nothing else to click. Put these fractions together to make this. We can cross multiply, I guess, to make this. And then I decide to rearrange this for x, which is pretty easy to do. You end up here. And now at this point we can just test the answers that were given and look for integer values of x because they both have to be integers. Now, when you're doing this, for 2 reasons, I'm going to test from this right side. If you're ever testing numbers in UKMT, I would suggest that you test from the right side because they know the questions in which you're going to test values. And so I'm convinced that they stick the correct answers towards the end of the list to make you waste time testing this way. So test from the other end, but also because this is asking for the maximum possible one, we must be testing from the right here. Because if you test from the left and 40 works, you still have to test 60 because it's bigger. Whereas if you test from the right here and this works, we immediately know the answer because that must be the biggest one. So we're going to test from the right here. If we put into 480 into this equation here, we end up with something times 23 on the bottom, which is obviously not going to cancel with anything up here. So that's not an integer. Next one, this looks much more promising because of this 400. And indeed, it does cancel to make a whole number because this is just a half and then half of 42 works. And so the answer will be 420. Now, I usually like cross numbers a lot, but this one ends up being absolutely horrendous. So what we're going to do is we start with the case that's the most, going to have the fewest options. And after a bit of thought, you realize it's going to be this one because 13 and 19 are co-prime. So the lowest common multiple is just what happens when you multiply them together, which you have to do, and you get this. And then the only other multiples of both of those numbers are just when you times this by 2, or times it by 3, or times it by 4. So there's only 4 cases here. And also, this one is wiped out because we can't use a digit twice, and so is this one. So it's either 247 or 741. Now, what do we do from here? Well, that number's either going to go here, 247, or 741. So we look at 1 across, and sorry, no we don't. We look at 3 across. 3 across is a square. Now, a useful fact about squares is that they're limited in their last digit, which is the thing shared with the 2 things that we have an option for here. A square number cannot end in a 7, right? So squares only end in these numbers, unless I missed one. I don't think I have, but they cannot end in a 7. So this thing has to be 741 because squares can end in 1. And now let's list the 3-digit squares that end in 1. The only way to make a square end in 1 is either to do things like 11 squared or 19 squared. So 11 squared, 19 squared, 21 squared, 29 squared, and 31 squared. So these are our options for this row. Again, we're going to get rid of some of these because that has a repeating digit, this has a repeating digit, and this has a 4, which we've already used. So we're down to these 2 now. We don't know which one it is. But the fact that they both have 6s in the middle is going to be helpful because that means we can now eliminate anything that has a 6 in it when we look at these 2. Now again, let's follow this vibe of using the most restrictive one first. Multiples of 11, there's going to be fewer of those than there are multiples of 9. And also, we know the multiple of 11, because it's going 1 down like this, has to end in the starting number of the square. So this multiple of 11 has to end in either 3 or 9. Now, how do you get multiples of 11 to end in 3 or 9? Well, you times them by something ending in a 3 or 9. Because the 11 has a last digit of 1, the last digit is just dictated by whatever you're timesing it by. So 11 times 13 will end in a 3, and 11 times 19 will end in a 9. So now let's list all the multiples of 11 that end in a 3 by doing 11 times 13, 11 times 23, 11 times 33, and so on. This is less painful than it seems because all you have to do is work out the first one and then add 110 a whole bunch of times, which is actually not that painful. We can now cross things out. You can cross out anything that repeats a digit. You can cross out anything that has a 4 or a 7 in it, and you can also cross out anything that has a 6 in it because the 6 is also being used here. That takes you down to only 2 options. And then you do the same thing, but this time testing the ones that end in 9, again by timesing by 19 or 29 or so on, 39 and so on. Again, you're just adding 110 a bunch of times once you work out the first one. Again, cross out anything that repeats a digit, cross out anything that has any of the digits you already used, and you're only down to 1 case if you do that. And now we basically just need to kind of, well, we could try testing these cases, but we have got the multiples of 9 left. Those things need to end in a 7. So again, how do you make a multiple of 9 end in a 7? Well, it turns out you just need to times it by something that ends in a 3, because like 9 times 3 is 27. That's the only way to do it. So this is 9 times 13, I believe. And then again, just add a bunch of 90s to get all of the other ones. And then again, cross out anything that repeats a digit, cross out anything that has a 4 in it, or anything that has a 6 in it. And you get all the way down to just one option if you do that, which is 297, I believe. I think all of the other ones just go away. Why was I getting rid of these? Why did they definitely not work? Oh, is it because I now cross-reference this? 1 across is a multiple of 9, 1 down is a multiple of 11. Sorry, yeah. The multiples of 11 have to start with either a 2, a 5, or a 5. So 2 or 5. So we're only interested here in things that start with a 2 or 5. So that's how we get rid of so many of these. We can't use a 0, so that one goes. So we're just down to these 2. This one has a 6 in it. We agreed that this number is definitely 6. So this one goes, and so this must be 297. And then you say, okay, well, we can only use the one starting with a 2. So that's 253, which means this one is 361, and the missing digit that we haven't used is an 8. And that was that question. Bit of a mouthful. Question 2 I really liked, question 22, because it just involves a lot of nice triangle work. Firstly, going from this corner, we notice that all 3 of these triangles essentially have the same perpendicular or same parallel base, and all have the same perpendicular height, which we could describe like this. Now, because this triangle is half the area of this one, that means this base must be half this base. Because the perpendicular height is the same, it's half times base times perpendicular height. Because the perpendicular height and the half are the same, this base here must be half of this base here. So if I just call this 1, this is 2. And same logic, this is now 3 times this area, so this length here must be 3 times. Sorry, this should be a 3. It doesn't end up mattering. Actually, I don't think any of this ends up mattering, but this should definitely be a 3. because it's 3 times the length of 4. So this should be 3 times whatever I labeled this. I could have labeled this as x, 2x, and 3x as well. None of this ends up mattering, I don't think, because essentially this trick is important, but it's not actually important right away, because now we think about this perpendicular height, which both this triangle, which is made of those 3 triangles, and this triangle share. Now, because this triangle is area, well, and actually the entire big triangle shares it as well, right? So you can think of it either way. Now, this triangle over here is area 24, and this triangle is area 8. The perpendicular height is shared, so this length must be 3 times this length. So let's just call this y, and this one 3y, which I should have done up here. I should really have just deleted all this stuff. It doesn't end up being important. But anyway, at this point, what we can do is we can draw the line to designate the triangle that we're actually thinking about. And we can say one more perpendicular height that's really relevant, if that's called z, is this perpendicular height here, from this parallel section to up here. Because now we have this triangle up here has area 12, and this triangle down here has area z. In fact, actually, what I'm going to do is I'm going to look at this whole triangle here, which has area 12 plus z. And this triangle here, just area z, I've called it. Now, because this whole triangle here has base 4y, that means that the whole area here must be 4 times the area of the triangle we're looking at, because the base is 4 times bigger and the perpendicular height is the same. So therefore, z, this area here, this z, must be a quarter of the whole area of this triangle, which is 12 plus z. Times everything by 4 and solve for z, and you end up with z is 4. Again, these sides don't end up mattering, but it was nice practice thinking about the things that I was just thinking about for the rest of the question. Now, the area of the whole thing here is 8 root 3. There are 8 of these, so each kite has area root 3, which means half of each kite is area root 3 over 2. Also, as we can see, this makes a perfect hexagon. Each of these angles must be 60, which means half of the angle is 30. We can use this now. This is basically all we need, because if we just label this side B and this side A, or vice versa, we can say a half times B times A is root 3 over 2, just from the area. And we can also say tan 30 is A over B. Tan 30 is 1 over root 3. So we can rearrange that for B. We can shove that result into here. We can cancel a lot of stuff down and end up with A as 1. Obviously, it can't be minus 1. Put that result in there and you end up with B as root 3. And then the whole perimeter of this shape is just a case of counting how many A's and how many B's you have. A is the shorter side, so we have 1, 2, 3, 4, 5, 6, 7, 8 of those, I think, if I counted correctly. So it's going to be one of the 8s, and you have 6 of the longer ones. It ends up being E when you count properly. I really like questions like 24. I just love function questions. I think they're great. The obvious thing to do here is to put in 3 into the function to get f of 3 plus f of 1 over 1 minus 3 equals 24 times 3. Now, this is minus a half, so you think, well, that wasn't very helpful. But now what you do is you put in minus a half to the original thing. Now, it might not be obvious why that's helpful. It cleans up to this. But now what you do is you put in 2/3 into the original thing. And quite magically, when you put in 2/3 to the second function, it turns out to be 3. And so if we call f of 3 x and f of minus a half y and f of 2/3 z, we just end up with some super easy equations to solve here. We can do this one minus this one maybe to get x minus y equals 28. And then we can add these two things together to get 2x equals 100, which means x is 50, and x is the thing that I labelled f of 3, so therefore the answer is 50. For question 25, this is a horrendous question, but the answer is there eventually. There's so much geometry you have to do here to really get this right. What I'm about to do is not the most efficient solution, but it is a solution. The first thing to know is that we can draw a line coming out here. This is a radius, just like this is. And this is 30 degrees here. The reason I know that is because this is also a radius down here, and this is also a radius, which means this is an equilateral triangle, which means if this is 30, then this is 30. So that's 30 there. If I then draw another one going up like this, I can then argue that this here is also an equilateral triangle, because this is a radius, and this is a radius, and this is a radius. So it's equilateral. We've already argued, so therefore this whole angle is 60. We've already argued that this angle is 30 here, which means this one is also 30, and we're good to go. So essentially, I did all of that just to argue this angle was 30. But now you notice this white kind of shape here is going to match perfectly with this part of the shaded region here. So let's just put this here, and then we end up with an identical sector to this one, That sector was, well, each semicircle has area 24. So this is a sixth of the semicircle, right? So 24 over 6 is 4. So this area is 4, which means this area is also 4, just by placing this curved section there, because they clearly match. So therefore that's 4. That's the easy bit. The hard bit is working out this area over here. Now at this point, just on the record, I would have 100% guessed the answer was 12, because clearly what they're going for here is area 444. Like it's just clear that that's what's happening. But anyway, let's prove it and actually get it right. What I'm going to do here is I'm going to split the area in half like this. And now I'm going to think about this triangle here. Now this is also equilateral, and I'll just prove it for a second. This angle here is 60 because it's double angle at the center of a circle to the edge. This is the angle at the edge here of this circle around here. This is the one in the center, so that's 60, double of 30. This angle here is also 60 because we just showed that there's an equilateral triangle here. So this is 60, which means this is also 60. These are both radii, so therefore these match, and therefore this matches as well. So this is definitely equilateral. So what we can do here is we can say that here's an equilateral triangle, and I'm just going to work out this area first. I need the radius of the circle. So firstly, the whole circle would be area 48. So 48 equals pi r squared divided by pi, and I'm not going to bother square rooting because it turns out all I ever need is r squared. Because to work out this top area up here, I'm just going to say that this is actually 60 over 360, which is of course a sixth. I'm just doing the area of the sector. So that's a sixth pi r squared minus a half times r times sine of the angle between them. Sine of 60 is root 3 over 2. So all this cancels down to be this. You can do the math yourself if you want to, but that's this little area up here. That's just the area of the sector minus the area of the triangle to make this here. So next I need to know this part of the area. And now what I decided to do here was to say that this area here, by symmetry, is clearly the same as this area here. Just because these curved sections match, this length is obviously the same, and because this is equilateral, these two angles, these two lengths are the same, so these areas match here. And so instead of working out the grey area, I'm going to work out the white area. And I can do that, again, similar to what we just did. I can work out the whole area of this triangle and then take away the sector that I already know has area 4. So this white area there is this whole triangle, which is a half times this radius, which is still 48 over pi because it's r squared, times sine of this 120 in between them. Sine of 120 is the same as sine 60, it's root 3 over 2, and then I'm just taking away 4 because that's the area of the sector as we worked out previously. That gives you this, and so these two areas together are this plus this. Obviously the 12 over pi is cancel and you get area 4, and so we're definitely correct. This has area 4, this has area 4, and this also has area 4, so the answer is 12. Thank you so much for watching, and I'll see you next time.